Tesla just revealed a major update in the evolution of its humanoid robot Optimus, and it's straight out of science fiction. According to the team, Optimus is now being trained on real-world videos, including public footage from platforms like YouTube. But it doesn't stop there. Tesla plans to soon incorporate third-party datasets at scale, effectively teaching Optimus how to understand and imitate a massive range of human activities, all through the same neural network architecture that powers Tesla's self-driving cars. In short, the robot is learning by watching us. This breakthrough is more than a clever hack, it's a paradigm shift. Instead of relying solely on labor-intensive motion capture rigs or human-annotated training data, Tesla is leveraging one of the richest and most chaotic sources of human behavior, the internet. The same videos we upload, everyday cooking tutorials, warehouse operations, people walking dogs, folding clothes, lifting boxes are now being turned into training material for a robot designed to replicate those tasks. It's multitask learning at industrial scale, and it marks a turning point in how general-purpose AI could evolve. At the core of this effort is a single, unified neural net and architecture Tesla has been refining for years through its full self-driving FSD system. The idea is that Optimus doesn't need task-specific code or hand-engineered modules for every type of movement. Instead, it can observe thousands of examples of a task and learn the patterns of motion, timing, and intent, just as the FSD AI learns from millions of hours of driving footage. This approach not only accelerates training, it makes the robot more flexible, capable of shifting between tasks without needing new code for each function. Imagine what this means. If a human posts a video of assembling furniture, and that video is clear enough, Optimus could eventually watch it, interpret the sequence of motions, and replicate it with no explicit instruction. The same applies to packaging products, stocking shelves, or assisting in medical prep work. Tesla is essentially turning the open web into a dynamic training simulator, and it sidesteps one of the biggest bottlenecks in robotics: the need for highly structured, slow-to-produce training environments. There are still major challenges. Videos on YouTube are messy. They vary in resolution, lighting, camera angles, and quality. Most are not filmed with robotics in mind. Tesla's AI has to learn not only what's happening in the footage, but also how to filter out distractions, recognize spatial layouts, and convert 2D visual input into actionable 3D motor plans. It's a monumental challenge in computer vision, language grounding, and robotics integration. But if it works, Tesla may leap ahead of traditional robotics labs, which still depend on narrow, clean lab environments and expensive simulation pipelines. This also places Tesla at the forefront of a broader shift in AI, the convergence of language, vision, and embodiment. As Optimus learns to match video observations with physical actions, it pushes the limits of multimodal learning. This is no longer just a robot that lifts boxes, it could become a system that watches, understands, and does. And it reinforces Elon Musk's claim that Optimus could eventually be worth more than the car business. But this strategy raises new questions. Where does Tesla draw the line in sourcing data? Will creators be notified their content is training AI? What happens when Optimus starts mimicking behaviors from video that aren't suitable for the workplace for safety? These are questions regulators haven't even begun to answer. But they're coming. Because if a robot can learn from the internet, it will inevitably reflect both the brilliance and the chaos of what's out there. For now, Tesla is forging ahead. The plan is to rapidly expand Optimus's capabilities through this self-learning pipeline, integrating more third-party data and using its own factories as proving grounds. If the approach succeeds, we may see the first truly adaptable commercial robot emerge not from a lab but from the same machine that once learned to drive by watching the road. Optimus is learning from US and soon. It might know more than we expect. In 2021, Elon Musk walked onto the Tesla AI Day stage and made a statement that stunned even his most ardent followers. He unveiled the Tesla Boater humanoid robot concept intended to take over what Musk called dangerous, repetitive, and boring tasks. At the time, many dismissed it as vaporware. But fast forward just a few years, and that sci-fi vision has taken its first mechanical steps into reality. By 2022, Tesla had a prototype. It wasn't graceful, but it walked barely. In the world of robotics, however, walking is no small feat. Then came Gen 2, revealed in late 2023. This wasn't just a robot stumbling around. It was cracking eggs, folding shirts, handling delicate objects, and dancing all with mechanical precision and remarkably human-like movement. 11 degrees of freedom in each hand, actuated fingers, and neural network training made this a far cry from anything Tesla had built before. The real progress came in 2024 and 2025. Tesla's engineers, using reinforcement learning and Tesla's own Dojo supercomputer, began training Optimus not in simulation, but in the real world. Footage from the Fremont factory showed the robot sweeping, vacuuming, stirring food, lifting industrial parts and doing so with balance and awareness. What's powering all this? Vision-based learning. Just like Tesla's full self-driving cars, Optimus doesn't rely on LiDAR or complex rule-based code. It learns by watching and repeating just like we do. Still, the robot isn't perfect. Critics point out that many demonstrations still require teleoperation, meaning a human in the loop. Its autonomy isn't as complete as the marketing implies. It can't navigate completely unpredictable environments with human-level fluidity, but the pace of progress is undeniable. In 2 years, Tesla went from a man in a spandex suit to a robot handling real-world tasks with mechanical reliability. Elon Musk isn't shy about his ambitions. In fact, he set a production target: 5,000 Optimus units by the end of 2025. Then scaling up to over 50,000 by 2026. The goal? To deploy them not just in Tesla's own gigafactories, but eventually in homes, offices, and even care facilities. The target price? Around $25,000 to $30,000 cheaper than most new cars and dramatically lower than anything Boston Dynamics offers today. But then Musk went even further. He proposed sending Optimus to Mars. Yes, Mars. Why? Because robots don't need oxygen. They don't complain. They can work 24 hours a day. On a planet where survival is a daily challenge, robots like Optimus could be the ideal pioneer sunloading cargo, building habitats, assembling solar arrays. In environments built for humans, a humanoid robot makes more sense than wheels or tracks. And SpaceX's Starship? It's designed with enough cargo capacity to send a small team of Optimus units on the next Mars cargo run. Tesla's internal AI systems give it a distinct advantage. The same Dojo supercomputer that trains the full self-driving neural nets is now training Optimus. It's an ecosystem: cars, robots, and eventually space-based systems learning from shared data. If one robot improves, they all do. Musk envisions a world where intelligent machines operate across Earth and Mars in tandem. But challenges remain. Scaling production from dozens to tens of thousands isn't just about hardware. It's about reliability, regulation, safety. These robots will operate in homes, around children, elderly people. Tesla will need to prove that Optimus won't just fold laundry, it won't knock over a person or malfunction in a way that causes harm. And from a business perspective, the question is whether consumers and businesses will find enough real-world value to justify the cost. Then there's the ethical dimension. If robots replace millions of human workers in warehouses, factories, or homes, what happens to those jobs? Musk has floated ideas like universal basic income, but society is far from consensus on how to handle that transition. A robot that can sweep a floor today could replace 10 janitors tomorrow. And yet, the potential is staggering. On Earth, Optimus could become a staple of elderly carelifting patients, preparing meals, even helping with mobility. In industry, it could run logistics lines 24/7, reducing human strain and injury. In households, it could wash dishes, carry groceries, maybe even entertain kids. And on Mars, if it really works, Optimus might be the first worker to walk across the Red Plains, laying the groundwork for the first human base. A machine designed for our environment, now reshaping another world. Tesla's journey with Optimus is still in its early chapters. But make no mistake, this is not science fiction anymore. It's science in motion. From egg-picking demos to interplanetary ambitions, Optimus is a bet on the future where humans and machines don't compete, but collaborate. Whether it becomes the most revolutionary labor tool since the steam engine, or just a flashy footnote in Tesla's timeline, will depend on how fast they can go from lab to life, one robot at a time. When evaluating Optimus, it's vital to understand Tesla's broader philosophy. Unlike traditional robotics firms that build task-specific machines like robotic arms for welding or vacuum bots for floors, Tesla aims to create a general-purpose humanoid that can operate in a world designed for humans. This is a much harder problem, but if solved, it offers exponential utility. The logic is straightforward. The world is built around human ergonomics. Door handles, stairs, tool interfaces, and vehicles are all optimized for our 2 arms, 10 fingers, upright posture, and 360-degree field of view. A robot that can mimic human movement doesn't need the world to adapt, it adapts to the world. That's why Optimus walks like us, sees like us, and manipulates the environment in a way our ancestors evolved to do. And Tesla isn't doing this in isolation. It's merging Optimus into a deeply interconnected software ecosystem. Neural networks trained on video data teach Optimus how to interact with real objects, while the same AI models used to navigate city streets are being adapted to process real-time environmental data. For example, a robot learning to open a door doesn't just rely on codates trained on thousands of hours of video footage and reinforced by success and failure, just like a child learning through experience. This approach is powered by Dojo, Tesla's in-house supercomputer. Originally built to handle the vast data needs of autonomous driving, Dojo has become the backbone for both Tesla vehicles and Tesla robots. It processes video, learns from millions of edge cases, and fine-tunes behaviors in real-time simulations before they're tested in the physical world. Few companies can match this kind of vertically integrated AI training infrastructure. Tesla also benefits from real-world testing environments, its own factories. Gigafactories serve as both training grounds and testing arenas. Instead of building robots in labs and hoping they work in the real world, Tesla is deploying them where they're needed, sweeping factory floors, moving parts, assisting in repetitive labor. Every interaction teaches the system something. Every failure becomes a new data point. But as impressive as this sounds, there are still limit-significant ones. Humanoid robots face physics problems that aren't easily overcome. Balancing while carrying uneven loads, walking on irregular surfaces, or reacting to unexpected events like a dropped tool or a human walking suddenly into its path, these are edge cases that require incredibly fast processing and nuanced decision-making. Even the most advanced neural networks today struggle with these on-the-fly adjustments. Optimus isn't immune. Moreover, battery life remains a constraint. Tesla hasn't disclosed precise specs, but based on similar robots, Optimus likely runs for just a few hours on a single charge. Weight, power management, and heat dissipation are active challenges. You can't have a robot working a full shift if it needs to recharge every 2 hours. And in a Martian environment, with extreme temperatures and limited power, this issue becomes even more critical. Then there's cost. While Musk aims for a $25,000 price point, that's ambitious. Most humanoid robots today cost between $100,000 and $200,000 to manufacture, not including software development. Mass production will bring prices down, but scaling to tens of thousands of units requires unprecedented manufacturing automation, something Tesla is still refining. The economics will dictate how fast these robots enter the mainstream. If a business can replace 3 workers with 1 robot, and that robot costs less than a year's salary for a human worker, the incentive becomes irresistible. But if the robot breaks down frequently, requires constant updates, or can't perform certain nuanced tasks, the return on investment starts to wobble. Tesla must make Optimus not just capable, but cost-effective. Yet, history teaches us that disruptive technologies often start out flawed. The first cars broke down constantly. The first smartphones were clunky. The first personal computers were little more than glorified calculators. What matters is not whether Optimus is perfect to date, whether it's improving faster than anyone else. And that appears to be happening. Tesla's roadmap shows clear milestones. Short-term, increase robot dexterity, reduce power consumption, and expand real-world use cases. Mid-term, deploy thousands of robots in Tesla factories. Long-term, consumer deployment and Martian integration. Each step is contingent on the one before it, but Musk has made a career out of collapsing timelines and challenging conventions. Still, deploying a humanoid robot on Mars isn't just about surviving the trip. It's about operating on another planet's surface. The thin Martian atmosphere, intense radiation, and sub-zero temperatures create a hostile environment for any machine. Motors seize, plastics become brittle, solar power is less efficient. Tesla will need to harden Optimus for these extreme-sousing space-rated components, autonomous failsafes, and maybe even nuclear or RTG-based power systems. But if successful, the implications are enormous. A team of robots could build the first Martian shelters, install solar panels, 3D print habitats, and lay out supply depots months or years before humans arrive. This reduces risk. It also reduces cost. Instead of sending astronauts to perform dangerous manual labor, robots can take the brunt of early-stage colonization. It's a blueprint for a fully robotic vanguard machines paving the way for a new world. Back on Earth, the social implications are no less dramatic. A society where labor is partially or fully automated could see radical shifts in employment, education, and social contracts. We may need to rethink work itself, what it means to contribute, to earn, to matter, when machines can replicate physical labor better and faster. In many ways, Optimus is not just a robot. It's a litmus test for how society handles the next wave of technological disruption. It's a mirror reflecting both our hopes and fears. Will we build a future of abundance, leisure, and creativity, one of displacement, inequality, and control? Tesla isn't answering those questions directly, but it is forcing us to ask them. And that's what makes Optimus more than a headline. It's the beginning of a new era where automation is embodied, where AI walks, and where our creations might one day take the first steps not just into our homes, but onto the red sands of Mars.